Hey guys, welcome back. Mr. Drew here, and we are continuing with our science lesson about phase changes and the graphs that accompany them. Before we get into that, though, let's take a look at the pseudo or real science behind some of the following events. It's really important that you can tell the difference between something scientific or pseudoscience. Let's take a look. Science or not, what's your best opinion about each of these? Made by aliens? How else could these crop circles have been possibly formed? Your zodiac sign. What does being born in the month of March actually tell you about you? The Earth looks flat. Here's evidence proving the moon landing was fake. The food pyramid. Is it important to eat all of these carbohydrates? Well, in each case, guys, some of these look scientific for sure, or they have scientific backing, but they're what we call pseudoscience. These are often things you might see on the internet or in a classroom sometimes in the case of the food pyramid, but it was more pseudo than real. Why is that? Well, pseudoscience attempts to solve a problem looking for evidence to support a claim, to come up with a certain idea. And in the case of moon landings, flat earthers, zodiac signs, and crop circles, wanting to think there's aliens or sell the fact that there's aliens, especially to people who are watching your YouTube channel on the internet, is a way to get views. Here's a modern way, that people create fake videos.
To help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs.
You see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele.
You might remember President Obama, but with video technology today, we can make it look like he's saying whatever we want to look like he's saying. So it's easy to be fooled, especially on the internet. And that's what I found these guys. These fellows who created the liquid mountaineering sport did a really great job of selling the ability to run on water. But are they actually running on water? Well, let's go ahead and take a look at how they made the amazing video.
What are we doing here?
We're selling the world a new sport.
Why?
Because the world needs something to believe in.
Well, High-Tech decided to look at a viral because we wanted to capture the spirit of the brand, we wanted to have some fun, and we wanted people to potentially think about High-Tech in a different way.
Basically, what High-Tech said to us was, it was a simple brief. They said to us, make us famous.
Well, High-Tech has a fantastic range of water-repellent shoes, which essentially we like to call shoes that hate water.
Actually, the idea was pretty simple. If they have these shoes that are that water repellent, well, then it would be possible to walk on water with it.
So we were really looking for like a way to make it look extremely real. This was a challenge for me. I've borrowed a lot of elements from the extreme sports films that we know.
It's speed, it's belief, and faith.
Sorry.
got the guys out there, got some guys who weren't even actors, just sports people. Go out there, shoot all day, all night. Everybody had cameras, we photographs, all this, lots of footage, extra stuff we could send out on the web as well to see the film properly.
You know, I really let them be the characters instead of like giving them lines. Just said, okay, you know, this is your reality.
Be on an angle there. We had like this floating system and on top of a stellage.
It's basically like a wooden construction that kind of moves along with the steps. So it's not just like, you know, plexiglass.
But it was with all these weights and stuff to keep it in place. We could adjust it with the inch.
Kind of goes with your steps while you go on, and that's why it looks so realistic.
And they felt like they walked on water. It was like real. It became real.
Can you believe it now? You see it in reality. Believe it, sunshine.
We got even a few of people saying, well, listen, I can do 5 steps now. Can you help me do 10? And we were like, no, that's not possible. But there are people
possible. Of course it's not possible. How could we run that fast, right? Sure looks good, though.
We don't necessarily suggest that you try this yourself.
We're just giving them something cool, something funny, something different. Yeah, we're having a laugh, but at the same time, I suppose there's an element of something real in it too.
It looks great. It looks so good. Unfortunately, guys, we're not able to run on the water. At least not at the speeds they're going. If you think about it, you can skip a stone across the water, but you weigh so much more than a stone. You'd have to be going that much faster and able to do this. So if you've ever been water skiing, you kind of are being skipped across the surface of the water, and some people can do it barefooted. But without the aid of a motorboat or something like that, there's just no way to get up the speed to overcome the gravity that would take you down into the water. So we would call this, for sure, pseudoscience, something that looks really real, really sold well to sell the shoes, but unfortunately not a real scientific idea. Too bad, though. All right, guys, let's continue on. We are working with some new things. Make sure you complete your phase change graph discussion, review packet, unit test next week. Your review packet is in the back of your packet, the last couple pages. Go ahead and work on that, and there'll be a folder up soon entitled Review to help you kind of go through and review the most important concepts. Today we're going to be addressing one of the more important concepts, which is how to read the phase change graphs like we made in the last class. If you remember, our question was, will the temperature of water increase steadily as it changes from solid liquid to gas, or do something different? In other words, what will happen to the temperature as we go through our phase changes? Take out your lab and let's see how we did completing our graph. Now we had choice A, a smooth and steady, choice B, something that looks like a staircase, choice C, and choice D. Which did you choose originally? And now looking back at your data, which is the correct answer? Which choice gives you the best indication of what happens to the temperature as we add heat energy to our material? Well, if I look through my graph should look something like this. And if I compare it to all the choices that I had, choice B is the correct answer. Now, almost nobody picks choice B because it has this strange shape. Why would the temperature stay the same for 2, 4, 6 minutes at 2 places on our graph? Why wouldn't the temperature just keep increasing? Well, something strange happens at these 2 points. And these 2 points are what we call the phase changes. This could represent melting, and this could represent vaporization. The temperature does not change during the phase change. And that's definitely not what we'd expect. Let's take a look and see why this happens and what's happening to the molecules in our experiment.
Dear Tim and Moby, what happens to matter when it changes states? Sincerely, Robert. I'd be happy to show you, Robert, but the last time we talked about the different states of matter, Moby was an absolute menace. You promise? No squirting me with water guns or dropping ice cubes down my pants. Okay then. Matter is anything that has mass and takes up space. And the basic states of matter are solid, liquid, and gas. Water is a good example of matter because its three states are all pretty common. Its solid form is ice, its liquid form is water, and its gaseous form is steam or water vapor. Like all matter, water changes states due to changes in temperature and pressure. But its chemical properties remain the same. A molecule of ice is the same as a molecule of water. State change is a purely physical change. Hey, I said no funny stuff. Give me the squirt gun. Molecules of ice are bonded tightly to one another in a structure called a crystal lattice. These molecules all contain energy, and that energy makes them vibrate. Wait a minute, where's the ice? Are you sure? You were going to put this in my pants, weren't you? When you heat the ice, you give these molecules more energy. They begin vibrating faster and faster. Finally, they break free of their bonds. When all the bonds have broken, the water molecules are free to flow past one another. And the ice is now liquid water. That's called melting. And the temperature at which a solid substance melts into a liquid is called its melting point. Every element or compound has its own unique melting point. The melting point of water is 0 degrees Celsius, or 32 degrees Fahrenheit. Check this out. If you stick a thermometer in the ice as it melts, you'll notice something interesting. The ice starts out at around minus 10 degrees, and as it's heated, the temperature climbs to 0 degrees Celsius. But then, it just stays at 0, even though the flame on the stove is on full blast.
This is important, guys. The temperature doesn't change. The ice is melting, but ice is always going to be 0, and it's not going to instantly turn to liquid water. It's going to take a while. That amount of time that's passing is why the temperature does not increase for a certain amount of time. The ice is going from solid to liquid, and it takes a while. And at that while, the temperature of the ice is 0. You cannot have warm ice. So, the temperature stays the same during the melting phase of water.
The temperature doesn't start rising again until all the ice melts. As long as there's some ice left, all that extra energy goes into breaking the bonds that hold the crystal lattice together. This extra energy is called the heat of fusion. Well, the process of turning a liquid into a gas is, hey, what's with the hose? The one that you're hiding behind your back. You better take it back outside before Mom flips out. Anyway, gas molecules have more energy than liquid molecules. Liquid molecules are attracted to one another and tend to clump together. But gas molecules bounce around randomly. To turn a liquid into a gas, you've got to add enough energy to overcome the forces of attraction between those molecules. That energy is called the heat of vaporization. When we add heat to water, its temperature rises until it hits the boiling point, the point where it starts turning into a gas. For water, that's 100 degrees Celsius, or 212 degrees Fahrenheit.
That's the boiling point. Think about it. Can you have water that's hotter than 100 degrees? No. Water that's hotter than 100 degrees is a gas. The liquid phase of water can only get up to 100 degrees. So, if you see a picture of boiling water, you know it's 100 degrees. And it's going to take a while for all of that water to turn to gas. And all of that time is why your graph has a flat part at 100 degrees. It will stay 100 degrees until all of that water is turned to a gas.
The temperature stays constant until all the water turns to vapor.
Wow. I think we just learned a lot about why our graph looks the way it does. Okay, now it's time to put everything together. Let's do our conclusion. The question is, what happens to the temperature as we heat the ice from a solid to a liquid to a gas? We need to make a claim based on what we found out. What's the answer to this question? What happens to the temperature as we go from solid to liquid to gas? In one sentence, the answer to that question is your claim. Go ahead and make your claim now if you don't already have one. You should be claiming that as ice solid is heated from liquid up to gas, the temperature rises. Sure does. But there are two places where it stays the same, remains constant, doesn't change. Now we need to provide evidence. Just like in English, when we make a claim, we need to support with evidence from the article. Now we're going to support with evidence from our lab. This needs to be a measurement, numbers, a value. What proves this statement? What are the values where the temperature remains constant? What are those values? How much time passed? Let's find out. Look at your data table and your graph. We see that this happens, my claim happens, when the ice melts at 0 degrees and water boils at 100. These are those two constant points we were talking about here. In our lab, I believe the ice was at 0 degrees for about 8 minutes and boiling after about 4 to 6 minutes, and then we stopped the experiment. So at 0 and 100 degrees, there is a certain amount of time that needs to pass. The temperature does not change. Why? Well, we just saw in Brain Pop the reason why. The reason why has to do with overcoming the attraction of the molecules together. In ice and in liquid, they want to stay together. The energy from the hot plate or from the flame is being used to break apart those attractions and to turn the phase from solid to liquid and liquid to gas. So it takes energy to do that. And that energy goes into breaking apart the molecules instead of raising the temperature. The temperature stays the same while the molecules are going farther apart as they change phase. Hopefully, you've got good claim evidence and reasoning for this experiment, because that will really help you understand the phase changes of matter. Now, when we look at phase change diagrams in general, notice all the sections. We have the section of solid. We have the flat, where we're melting. Now we're a liquid and we're rising again in temperature, and then we're boiling, and then a gas. So there's a lot you can do, and you have this in your packet to understand how these phase change graphs work. Notice the line's not straight. There are 5 segments. We've labeled them A through E. When the line's moving up, such as here, what looks like a diagonal, we have temperature increasing. However, there are flat places where the temperature does not change. The temperature here for water is 0. The temperature here is 100. It does not change until all of the ice is melted or all of the water has been turned to a gas. You could take a pen or pencil or label these terms or color them, such as you have in your packet here. Color the area that is solid ice blue. If you have colors, go ahead and do this. And go ahead and answer the questions. Pause the video, come back in a few minutes, and let's take a look at your graph now. Now we've colored in the different parts of the graph so that we know where the solid, liquid, gas are, the melting, and boiling point. Now it's important to see that if we go in the other direction, if we reverse everything, we are condensing from gas to liquid or freezing or solidifying liquid into solid. Okay. Here are some questions we need to know. Is there a change in temperature at the melting point? You need to be able to find the melting point. Here it is at B. Notice that this is flat. A lot of people say that when you melt something, you're adding heat, which you are, but the temperature does not change. Ice does not increase from 0 degrees to 10 degrees because warm ice doesn't exist. The temperature while it's melting is 0. Is there a change in temperature when the material is a liquid? Yes, we can definitely heat up a liquid. But how about at the boiling point? To boil water, we need to raise the temperature of the liquid to this boiling point. But at this point, we cannot raise the temperature. So there's tricky questions that you could be asked, such as, does the temperature of a material increase while it's boiling? No. While it's boiling, it stays at, in the case of water, 100 degrees. And all materials have their own graphs that look much the same. 2 flat portions where melting and boiling occur. So make sure you understand that, and make sure you are clear on the next things that we're going to do. If you can answer these questions, all the better. You have a review packet in your packet to get ready for your unit test, which is coming very soon. The next time I will see you, we'll be going over the review packet looking at some answers. And then the time after that, we'll be taking our test for Unit 2 and wrapping up properties of matter. Hope you enjoyed it. And thanks so much for joining us back here. And Trying Science, we'll see you next time. Bye.